Okay, so let's start. Recall that we were trying to prove or at least characterize when is an infinite hypothesis class pack learnable, at least in the context of binary classification, right? And for this, we defined a number of quantities, which I said were measures of complexity of a particular hypothesis class. The first quantity that we defined was the VC dimension of a hypothesis class, and that is essentially the size of the largest subset of the domain which is shattered by the hypothesis class H, right? And very closely related was this growth function, which is essentially a function of m or n. So the growth function phi h of m is the size of the largest subset of xm, or the size of the largest restriction of the hypothesis class among all subsets of size m. And as we saw, if the VC dimension of a hypothesis class is d, then the growth function is equal to 2 to the power m if m is less than or equal to d, and it is strictly less than 2 to the power m if m is greater than d, right? And ultimately, our goal was to prove this fundamental theorem of pack learning, which gives a number of equivalent conditions for a particular H to be pack learnable. And in particular, we were trying to prove that if a hypothesis class has finite VC dimension, then it has the uniform convergence property, and therefore it is pack learnable. And I also claimed that for binary classification, the sample complexity of agnostic pack learning can be upper and lower bounded by some constant times d plus log 1 over delta divided by epsilon square. Now, we won't prove this particular, in fact, we won't prove the lower bound at all in this course. But even for the upper bound, we won't prove something which is exactly equal to this, but we'll prove something close to this. So we'll show that some constant times some function of d, something that grows roughly like d log d. But it's almost the same as what we have over here. All right. So in order to prove this, I want to introduce this new quantity called the rademacher complexity of a particular hypothesis class. So recall that for every hypothesis H, I defined the function g of x comma y to be just the loss on x comma y when I use the hypothesis H, right? So if h of x is the prediction corresponding to x under hypothesis H, then g of x comma y is simply the loss that H incurs when this particular sample x comma y was observed, right? And using this, I defined the empirical rademacher complexity, which is this weird looking quantity. It looks something like it looks like a weighted empirical risk, right? It's not exactly equal to the empirical risk, but the terms of the empirical risk are weighted by plus minus 1 random variables. And then you take the maximum over all possible hypothesis, or in other words, all possible g, and take an expectation over the Rademacher random variable sigma. Right? So this is what I call the empirical Rademacher complexity, but this is a random variable that depends on the sample, on the training set, and we can define the Rademacher complexity as simply the expectation of the empirical Rademacher complexity taken over essentially taken over the samples, right? So it's expectation over S distributed according to Pxy with n samples, right? IID Pxy. And the goal of this class will be to try to prove the following theorem, which says that if given any supervised learning problem with a bounded loss function, then we have the following, that with probability greater than or equal to 1 minus delta, the generalization error for every hypothesis is upper bounded by the empirical risk plus twice the rademacher complexity plus some quantity that depends on delta and n. Right? And in particular, if the rademacher complexity is something that decays with n, then we have essentially we'll have the uniform convergence property. Right? So yes. Which one? It is not with respect to, so this one is with respect to a particular training set, but this is the rademacher complexity, so it depends on the distribution pxy, but it doesn't, but it's not a random variable, it's a deterministic quantity.
Based on taking some of length n.
It's an expectation, right? Correct. So it's, so this basically depends on of course the hypothesis class H, the loss function L. It depends on the corresponding distribution pxy, and it depends on the size of the training set, but nothing else. Right? So if the rademacher complexity decays with n for every distribution, then we'll have the uniform convergence property. Okay, so because this particular rademacher complexity depends on the distribution pxy, it's defined for a given pxy. Any questions? Great. So the key ingredient for proving this will be the bounded differences property that we saw in the concentration inequalities course, and McDermott's inequality, which gives a tail bound, an exponential tail bound for functions with bounded differences. Right. So let's quickly recall what that was. So a function f on n variables has the bounded differences property if essentially any change of the ith variable can lead to the function value changing by an amount at most ci. So no matter what the configuration of x1 through xn is, if I change xi, I replace xi with any other xi prime, then the value of the function can change by at most ci, plus or minus ci. All right. So this is when the function has the bounded differences property, and the corresponding constants is we'll denote this by c1 through cn. And we saw, I mean, we didn't prove it in the concentration inequalities course. We only saw the Efronstein inequality, but I did state the McDermott's inequality, which says that if f has the bounded differences property and x1 through xn are independent random variables, again we might as well assume that they're independent and identically distributed, then for every epsilon greater than 0, the probability that f of x1 through xn deviates from its expectation by an amount, let's say in the positive direction, by an amount the epsilon, is upper bounded by e to the power of minus 2 epsilon square divided by summation I equal to 1 to n ci square. All right, so this is for the positive tail. The negative tail can also be bounded as follows. So the probability that f of x1 through xn minus expected value of f of x1 through xn is less than or equal to minus epsilon is also upper bounded by the same quantity. right? So what can you say about the random variable f of x1 through xn? What property does it satisfy? No, not necessarily. The tail bounds are symmetric. It's only a bound, right? F is a sub-Gaussian random variable, right? Because we have e to the minus some constant times epsilon square for every epsilon greater than 0. F need not be bounded, right? I have not assumed anything about the domain set X.
It's bounded.
It has boundary differences, yes. Um, how do you prove that? Okay, try proving it separately as an X. That's there, but then it doesn't tell you for to show that f is a bounded random variable. You have to show that f of x1 through xn is between, say, minus some little m and capital M with probability 1. This will not give you a particular property. But anyway, we will be dealing with bounded functions. That's why we'll ultimately get the bounded differences property. But this is general enough.
So it is not true of x may be bounded.
Check. Check. Right? Okay. Okay. So now let's again recall what we want to show. We want to show an upper bound on the generalization error of a particular hypothesis, right? So let's fix in fact, let's not fix a hypothesis class. Let us just fix a distribution. We'll fix n, we'll fix pxy. And for this, I'll define so for every training set, I'll define the following random variable phi of s, which is the supremum overall h in h of essentially the deviation of the empirical risk from the generalization error. And for this, I look at r of h minus rs of h. Okay, great. Now the first point is that I claim that no, again, all the randomness in this is coming because of the training set, which are IID. The samples are all IID, and even though this can be represented as a sum of IID random variables, because of this supremum, P of S is not a sum of IID random variables anymore, right? Because I have a supremum over all possible h. For a given h, this quantity is a sum of IID random variables. The first claim is that P of S has the bounded differences property. Okay, so how do we prove this? Let's assume that, so we have S, which is x1, y1 up to xn, yn. You have n pairs of random variables. And let's assume that S prime is obtained by only changing the ith random variable. Right, so S is some configuration, and S prime is obtained by replacing xi yi with a new sample xi prime yi prime. So let's look at P of S minus P of S prime. What is this? This is supremum over all H in H R of H minus Rs of H minus supremum over all H in H R of H minus Rs prime of H. Okay, so the H that achieves the supremum in this could be different from the H that achieves the supremum in this. But I claim that this is less than or equal to the supremum over all H in H of R of H minus Rs of H minus R of H minus Rs prime of H. Why is that true?
That's access to H for the first term.
Correct.
Like, put that H in the like second term, always going to be less than or equal to the supremum of H. Capital H. It's a negative.
Correct. So basically I'm using the property that maximum of A minus maximum of B is less than or equal to maximum of A minus B, right? When the maximum is taken over all A and B. Okay, great. But what is this equal to? The R of H just cancels out. So this is supremum over all H in H of Rs prime of H minus Rs of H, right? But what is Rs prime of H minus Rs of H?
This part.
It only contains the ith point, right? So this is nothing but G of, or in other words, L of H of xi yi minus L of H of xi prime yi prime, the other way around. So it's going to be G of xi prime yi prime minus G of xi yi divided by n. So 1 by n also sitting there. For any H, what is the maximum value this can take? One by n, right? Because the loss, I've assumed that the loss function is bounded between 0 and 1. So the maximum is achieved when this is equal to 1 and this is equal to 0. Okay, so This means that phi has the bounded differences property.
0, 1.
We've assumed any loss function which is bounded between 0 and 1. It need not be the 0, 1 loss. It need not even be a classification problem. So far, none of that assumption is required. Any loss function which can be bounded. If it's bounded between two other numbers, then this would be whatever, the maximum minus the minimum. Then this particular approach doesn't work, but things can be generalized. Ultimately, all you need is you have to ultimately be able to apply some kind of a sub-Gaussian or a sub-exponential tail path. But in most cases, bounded loss functions is reasonable. Particularly if you're restricting yourself to certain domains. Okay, so now I can apply the McDermott's inequality. So what is the probability that P of S minus expected value P of S is greater than or equal to epsilon? This is less than or equal to e to the power minus 2 epsilon square divided by summation ci square. Each ci is just 1 over n, so this is 1 over n square. You're summing over n terms, so this whole term becomes just 1 by n. This is just e to the power minus 2n epsilon square. Okay. So now if I want this to be at most, say, delta, then if this is equal to delta, then what should epsilon be? Log will be 1 over 2n times log 1 by 2n log 1 over delta. Correct. Right, so I can say that the probability P of S minus expectation P of S is greater than or equal to square root log 1 over delta divided by 2n is at most delta. Okay, so now all that remains is to prove a bound on expected value of P of S. So let me call this equation 1. Okay, we'll use similar tricks as before. So what is expected value of P of S? This is expectation with respect to S of supremum over all possible hypotheses of R of H minus Rs of H. right? My end goal is to somehow show that the right hand side is related to the Rademacher complexity. So I need to somehow be able to introduce these plus minus one random variables. So first what I do is I have supremum over all h. I can write r of h. What is r of h? It's just expected value of rs of h, right? I can write this as expected value with respect to some other training set, which is IID, let's say independent of S, rs prime of h minus rs of h. Where S prime is independent and identically distributed according to Pxy and is also independent of S. So it's a fresh training set.
The expectation.
Correct.
The generalization, the value of the loss.
The expected value of correct.
Whereas in the RS stretch, there is an extra 1 by n.
But it's a sum over n terms, right? So let's just write it down. Expected S prime of rs prime of h is nothing but expected value of S prime of 1 over n summation I equal to 1 to n L of h of xi prime yi prime, right? So it's nothing but 1 over n summation I equal to 1 to n expectation of L of h of xi prime yi prime okay. Okay, that's good. Now I have expected value of P of S to be equal to this. I'll again make use of the fact that the supremum of A plus B is less than or equal to supremum of A plus supremum of B. So that will allow me to take this expectation outside. So this is expectation with respect to x, S, expectation with respect to S prime of supremum overall h in h, rs prime of h minus rs of h. Let's just write this, expand this out. This is 1 over n summation I equal to 1 to n L of h of xi yi minus L of h of xi yi prime, or this is just g of xi prime yi prime minus g of xi yi. Okay, so with respect to s, expectation with respect to s prime. Now s prime and s are independent and identically distributed, right? Claim that this is equal to h 1 over n 1 to 1 to n. Now g of xi, let's look at, for a given I, let's look at this particular quantity. This is a random variable, right? Whether you look at g of xi prime yi prime minus g of xi yi, or g of xi yi minus g of xi prime yi prime, will the distribution change? So let me call this, say, psi of xi yi xi prime yi prime. Okay, is psi of xi yi xi prime yi prime symmetric? Why? So xi prime yi prime is independent and identically distributed as xi yi.
They're summing over only g of x.
Let's assume I'm looking at one particular term in the summation. If you fix any particular term in the summation, whether I look at this quantity or the negative of this quantity, I claim that it ultimately doesn't influence this overall expectation. Okay, and why?
Because g is a loss of
I claim that that doesn't matter whether it's bounded or not. So ultimately, let's just look at this. Right? Let's look at this. Since S and S prime are independent and identically distributed, even if I take the negative, so let me write out what I want to write. This is equal to sigma I times g of xi yi or xi prime yi prime minus g of xi yi for any sigma 1 through sigma n, which are either plus 1 or minus 1. The reason why this supremum doesn't change whether I have sigma I to be +1 or -1 is because if it is a -1, then I can just swap the roles of xi prime and yi prime, of xi yi with xi prime yi prime, right? Because they're independent and identically distributed. So xi prime yi prime and xi yi for this particular quantity, they're just labels, right? Nothing else. They're essentially identically distributed and they can be interchanged. So this supremum is equal to this particular supremum, or the distribution of this particular supremum is equal to the distribution of this particular supremum. This is of course assuming that each sigma I is either +1 or -1. And since this is true for every configuration, it's also true for a random configuration. So this is equal to expectation over S, expectation over S prime, expectation over sigma of supremum over all H, 1 over N, I equal to 1 to N, sigma I times G of xi prime yi prime minus G of xi y prime.
Taking expectation over all S and prime are basically the same.
I'm sorry?
And S prime are just distributed over Px y itself, right?
Correct.
Taking expectation over S similar to taking expectation over S itself. The latter thing.
Correct, but one thing you have to keep in mind is that there are two n pairs of random variables here, right?
Yeah.
So, but everything is independent and identically distributed.
Like xi prime and xi are basically kind of like IID.
They are IID.
Same distribution.
They're exactly IID.
That's why it doesn't matter.
That is why it doesn't matter in this case. Okay. Now I'm again going to use the bound that maximum of x minus y is at most maximum of x plus maximum of y. Right? Any questions? Yeah.
Like, how can we prove this that like the first equality we have written, like for introducing sigma?
For introducing sigma. Basically, why this is equal to this.
Yes. Like, how can we prove it rigorously?
How can you prove it rigorously? Okay, so let's let's look at ultimately what do I want to show. I want to show that this expectation. Okay, so let's focus on suppose n is equal to 1. I want to show that expectation with respect to S prime of supremum over all H in H, let's say G of xy minus G of x prime y prime is equal to expectation over S prime of supremum over all H of G of x prime y prime minus G of xy.
We are renaming it. Like we can rename S and S dash.
Correct.
And we can like interchange the expectation.
Correct.
But how will we like if we do this for generalization?
Yes.
Then we can then it will become like we are negating all the values. Like we are negating in the summation which would be inside when 1 by n summation.
So if you're okay with this, right, it's the same as the previous case. Why? Because again, you have expected value of S prime of supremum H in H. Let's assume that some of them are positive and some of them are negative, right? So firstly, let's take summation I equal to 1 to n of G of xi yi minus G of xi prime yi prime. I want to show that this is equal to expected value of overall S prime of supremum overall H summation overall I sigma I of G of xi yi minus G of xi prime yi prime, right? So basically if all of the sigma i's are positive, then the two are exactly the same, right? So for all sigma I which are less than 0, you just interchange xi prime yi prime with xi yi. That's it. That's all. Again, I'm heavily relying on the fact that all of the xi yi's, all of the xi prime yi primes, they're all independent and identically distributed.
Expectation with this the sample set.
Correct.
It's the meaning is like the underlying distribution of that sample set.
Yes.
The pxy from which you are generating the S and S square.
Correct. Yes. So this, in particular, this expectation subscript S doesn't denote conditional expectation or anything. So essentially, the subscript denotes which random variable I'm averaging over.
With sample and come to inside the multiply the probable percent, but you do all the rest you can think of.
I mean, this quantity is nothing but integral overall xn yn integral overall xn whatever xn prime x prime n y prime n f. So they're all IIT, right? Times this particular function. For a given, the quantity inside the brackets is a random variable. It's a function, this is basically a function of two n random variables, right? There are n xi yi's and n xi prime yi primes. Which one? It's because I just exchange the roles of xi prime yi prime with xi by I, nothing else. Right? Essentially, these are, so what I want to know is, does this expectation change whether, okay, so let's look at just for notation, let's without loss of generality, let's just assume that we have some random variable or some function which is indexed by h, okay, and this depends on x or xi. We call these zi. So zi is xi prime yi prime or xi yi, right? So this is just g of xi y. Okay, now what do I have? I want to know what is so g is a deterministic function that depends on h. Xi yi are random variables. But they are random variables, right? We're looking at random samples. I'm sorry? These are random variables, yes. We are fixing an arbitrary distribution. We don't care what the distribution is. Right? Initially, we assume that there is it doesn't matter. So, irrespective of what the underlying distribution is, I want to make some statement about this P of S, right?
Is it because we don't care about the sample?
XI is always a random variable. There's no doubt about that, right? It is just that I'm making a statement. I'm saying that the same statement holds irrespective of what the distribution of xi by I is. Right? That's what I'm trying to prove, some kind of a uniform convergence result. It says that for every pxy, this holds. right? It's not true for, so all of the quantities, of course, the kind of, over here, I still don't have a uniform convergence property. Yeah. So here I don't have a uniform convergence property. This bound depends on Pxy. This, and the way it depends on Pxy is through this quantity, the Rademacher complexity. Right? For a different Pxy, I get something, this quantity differs. So the overall bound also changes. Right? But that's okay. So all of the dependence of this bound is fully captured by this single term, the Rademacher complexity. Does that make sense? Okay. So where was I? Yeah. So right now we're trying to prove the try to derive an upper bound on the expected value of P of S, right? And we're almost there. So this bound that we have, we saw that phi of S, or expected value of P of S, is upper bounded by this. But what is the first term equal to? Expectation with respect to S, P of S is expected value with respect to S, expected value, or S prime, expected value with respect to sigma, supremum overall H, 1 over n, I equal to 1 to n, sigma I, g of xi prime yi prime, plus expectation with respect to S, expectation with respect to sigma of supremum overall H, 1 over n, summation I equal to 1 to n, sigma I, g of xi yi. What is this? That's the empirical Rademacher complexity. And when I take the expectation with respect to x, I get the Rademacher complexity. And the same holds for both of these terms. So this is just 2 times the Rademacher complexity of G. Okay, so let's use this in equation 1. Right. So earlier we showed that let me just write this in a different way. This is less than or equal to, this is greater than or equal to 1 minus delta. I'm just taking the negative of the statement that I had in equation 1, or so this is what we had earlier. Right? The probability that phi of S is less than or equal to expected value of phi of S um, plus square root of log 1 over delta by 2n is at least 1 over delta. And we also have an upper bound on expectation of phi of s. So if this holds for expectation of phi of s, it also holds for any upper bound on expectation of phi of s. So the probability that phi of s is less than or equal to 2 times the rademacher complexity plus square root log 1 over delta by 2n, this is at least 1 over delta. You mean how I get this from this? So let's look at this particular event, right? If phi of s is less than or equal to some number, then for sure phi of s is less than or equal to anything which is greater than this number, right? And I know that this is greater than or equal to this. That is why this is the following notes. Is that okay? That's okay. I just want a lower bound, right? So what I have is, let's call this number, let's call this alpha, and let us call this beta, right? I know that alpha is less than or equal to beta. So P of s is less than or equal to alpha is a subset of all s such that P of s is less than or equal to beta, right? So the probability of this is greater than or equal to the probability of this. So therefore this bound automatically holds. Yeah.
The RC of the number is great.
The
loss function can take effect.
The loss function, I'm assuming the loss function is always non-negative. Right? The loss function is between 0 and 1. That is the assumption. And in general, we always assume that the loss function is non-negative. Whether it's bounded by 1 or not, it's at least 0.
Bounded between A and B.
I always assume that A is greater than or equal to 0. Yes. I mean, even otherwise, I could always shift everything by A, even if A is negative. Okay, but what is phi of s? Yeah. Which part? You mean how I get this from this? Okay, so let me call this random variable. Okay, let's call this random variable x, or let me call this alpha. Let's say this is alpha, just this term. and this is beta, right? So what I have over here is supremum over all h of alpha minus beta, right? I claim that this is less than or equal to supremum of, okay, let me do it in 2 steps. So I have supremum over all h of alpha whatever minus beta, right? This is, what can you say about this compared to supremum over all h of alpha minus, let me call this plus, supremum over all h of beta. Look at this, great. Okay, great. So let's look at, I have supremum over all h of summation I g of xi prime by I prime sigma I by n minus summation over all I sigma I g of xi yi divided by n. Okay, so using this, what would be the most natural bound that you would get? Fine, let's suppose that let's take that. So supremum over all h of summation over all I sigma I g of xi prime yi prime by n minus, let's say, plus supremum over all h of summation over all I, let's say minus sigma I g of xi yi divided by n. You're satisfied with this, correct? Okay, sorry, minus here, correct? But I have an expectation with respect to sigma. So sigma i's are random variables which are plus or minus 1 probability have the same distribution. That's it. Any other questions? Okay. If not for the expectation, yes. So it doesn't hold for arbitrary sigmas. So I'm using the fact that these are ID rademacher random variables, they're symmetric, everything is nice. Okay, where was I? Okay, fine. So this I've shown that this is true, which implies that the probability that for all h r of h is less than or equal to rs of h plus 2 times the rademacher complexity of g plus square root log 1 by delta by 2n is greater than or equal to 1 minus delta, right? Which was basically the first part of the theorem that I wanted to prove. Any questions? Okay. So I won't prove the second part of the theorem. Right. So we've shown this. Correct. And the second part of the theorem involves two steps. The first is exactly what we've seen so far, which is so for part two, again, we first derive the same bound, but with delta by 2. All right. So the probability that P of S is, let me just copy this. Or in fact, I might as well just use this. P of S is less than or equal to delta. This is what we showed, right? This is what we've already shown. If I want to choose a delta by 2, then you get just a log 2 over delta over here. Okay, so this is something that you can show directly from what we've seen so far. The only other step is to show that the probability that R the S of G, which is the empirical Rademacher complexity, deviates from the Rademacher complexity by an amount of log 2 by delta by 2n. We show that this is less than or equal to delta by 2, some constant C prime times this. All right. So you know that this holds with probability at least delta by 2. And you know that the empirical Rademacher complexity is very close to the Rademacher complexity with high probability, or probability that deviates is at most delta by 2. And then you just use the union bound. Right. So the probability that phi of S is greater than or equal to 2 times the empirical Rademacher complexity plus something else. It's not exactly this. It is this plus this is bounded by delta. Okay. Of course, now you need to show that the empirical Rademacher complexity is close to the true Rademacher complexity. And once again, you just show that the empirical Rademacher complexity is a bounded differences function. Okay. So far, at least this particular result did not assume that we're talking about binary classification. It holds true for any supervised learning with bounded loss functions, right? So what happens if we restrict ourselves to binary classification? So for binary classification, we can derive an upper bound on the rademacher complexity in terms of the growth function. So we can show that this is less than or equal to square root of 2 times log of the growth function by h of n whole divided by n. Okay, and the proof involves again some properties of sub-Gaussian random variables. I don't remember if I had given this as a homework or not in the concentration inequalities course. But essentially you can bound the expectation of the maximum of a sum of random variables using the sub-Gaussian constant. So what you can show is the following lemma, which says that if you have a subset of say Rn which is finite, and let's say that R is maximum overall x in A of the norm of x, the 2 norm of x, then expectation overall sigma, where the sigma are IID Rademacher random variables, of 1 over n maximum overall possible x of I equal to 1 to n sigma I xi is upper bounded by r times square root of 2 times log of size of A divided by n. A is a finite subset of Rn. For now, let's assume that this lemma is true. What is the Rademacher complexity equal to? This is equal to expectation over S, expectation over sigma of 1 over n supremum over all h in h of summation I equal to 1 to n sigma I g of xi yi, right? Can I use this lemma? I, I claim that I don't need h to be finite. Okay, suppose that h were finite, then you can immediately see the connection, right? Because I have this g of xi yi, I can call this xi, and then I can directly apply Massar's lemma. Correct? But now, where does the problem lie? Yes,
Then you utilize that
correct. So let's fix a particular s, okay? Because anyway, this whole thing depends on one particular choice of s, right? So for a given s, what is this maximization taken over? Exactly. So effectively, for a given s, this maximization is not really over all of h. It's over the restriction of h to s, right? So this is equal to expectation over s, expectation over sigma of 1 over n supremum or maximum over all h in the restriction of h to s of summation I equal to 1 to n sigma I g of xi yi. Right? Now I can apply the lemma. This is less than or equal to expectation over s of, now what is r? What is the maximum L2 norm of this? It's a 0-1 loss function. It's a 0-1 loss function. So g of xi yi is either 0 or 1. So if I stack the vector of g of xi yi's, the norm is going to be at most root n, right? So this is expectation over s of square root of n times square root 2 times, what is a? A is basically hs, right? And what is the maximum value that hs can take over all possible s? The growth function, right? So this is just by definition, this is equal to the growth function because I'm fixing the number of samples. Right? Let's see if slight mistake. This square root in the lemma does not extend to the denominator. Okay. Any questions? Which one?
Less than or equal to.
Here. So it's square root n because of the r.
There is one.
There's a whole divided by n. There's a whole divided by n. And this. Okay. What would be the cardinality of A? Well, A is equal to HS, right? For a given S, okay, for a given n, what is the maximum value that the size of HS can take? Correct, which is the growth function, right? So now if I combine this with the previous lemma, I get that now I have a bound on the rademacher complexity in terms of the growth function. Correct. So it's an upper bound anyway. So R of H is greater than or equal to Rs of H plus square root 2 log of the growth function divided by n plus square root log 1 over delta by 2n. This is at most delta. So now I have bound on the generalization error in terms of the growth function. What is the largest value the growth function can take? 2 to the power n, right? So the largest this can be is a constant. Then this is no longer useful, right? Because after all, R of H can only be between 0 and 1. So this bound becomes completely useless if the growth function is equal to 2 to the power of n. Okay. So in the next class, we'll connect the growth function to the VC dimension, and that will complete the proof of the fundamental theorem of path learning. Any questions? Okay, so let's stop here. Why will it be? Because then you would have Rs of H. Rs of H is again something that is between 0 and 1. This would be root 2. Which I mean, R of H can never be greater than root 2. So this is a trivial bound. This becomes interesting only if this is something that is really, really small.